For most of human history, reality felt stable. A rock stayed where you left it. A light switch was either on or off. Cause came before effect. The world behaved like a machine with predictable rules. Even when scientists discovered atoms, electricity, and relativity, there was still an assumption underneath everything. Reality itself existed in a definite state, whether anyone looked at it or not. Quantum mechanics shattered that assumption over a century ago, but for decades many physicists treated its strangest implications like mathematical annoyances. The equations worked, the experiments matched, and technology advanced, so most people avoided asking the deeper question: what is quantum mechanics actually saying about reality? Now, quantum computers are forcing that question back into the open. These machines are not just faster computers. They operate using behaviors that should not make sense in ordinary reality. A quantum processor can explore enormous numbers of possibilities simultaneously, using superposition and entanglement in ways classical physics cannot explain intuitively. And as these systems become more powerful, some physicists are becoming increasingly uncomfortable with what their success may imply. Because if quantum computers truly work the way our equations say they do, then reality may not be singular, local, or even fully objective. The horrifying part is not that physics found something evil. It is that the universe may be far stranger than the human brain was built to handle. In 2025, quantum computing researchers announced results that sounded less like computer science and more like a direct attack on common sense. The experiments were designed to answer a technical question: are quantum computers truly using quantum mechanics, or are they somehow faking it through hidden classical processes? But the deeper implication turned out to be much stranger. The machines passed the tests. And that matters because quantum mechanics has always carried a disturbing possibility inside it. Physical reality may not exist in a fully definite state before interaction. To understand why this caused such a reaction, you have to look at what scientists were testing. Quantum computers use qubits instead of normal computer bits. A classical bit is simple. It is either a 0 or a 1. A qubit behaves differently. According to quantum mechanics, it can exist in a combination of states simultaneously until measurement forces a final result. That idea has bothered physicists for nearly a century. Einstein especially hated it. He believed quantum theory had to be incomplete because nature, in his view, should contain definite properties whether humans measure them or not. A particle should already know where it is and what state it's in, but experiment after experiment keeps weakening that assumption. The newest tests focused on entanglement, the phenomenon Einstein called spooky action at a distance. When particles become entangled, their properties remain mathematically connected even when separated. Measuring one instantly changes what can be predicted about the other. Quantum computers depend on this effect to perform calculations impossible for ordinary machines. Researchers created protocols that essentially acted like lie detectors for quantum processors. If the computers were secretly operating classically underneath, the statistical patterns would reveal it. But the correlations matched genuine quantum predictions instead. That means the strange behavior is probably not an illusion caused by missing information. The particles do not appear to carry hidden classical instructions waiting to be uncovered. Instead, the probabilities themselves seem fundamental to reality. That is the part people find horrifying. Because humans naturally assume the universe behaves like a completed picture at all times. You expect objects to possess definite properties, even when nobody looks at them. Quantum mechanics keeps suggesting that assumption may only work at large scales because countless interactions constantly stabilize reality around us. At microscopic scales, things become far less clear. A quantum particle can behave like multiple possibilities at once. It can interfere with itself. It can remain mathematically undefined until interaction occurs. And now humanity is building machines that function only because this bizarre framework is real. Quantum computers are not proving magic. They are not proving consciousness creates the universe. But they are forcing physicists to confront something deeply uncomfortable. The world underneath everyday experience may not operate with fixed certainty at all. And every improvement in quantum computing pushes that conclusion harder. Because if the underlying reality were truly classical and deterministic in the normal sense, these machines should not work the way they do. But they do. One reason quantum mechanics sounds unbelievable is because nothing in normal human experience prepares you for it. You wake up in the same room every morning. A chair stays where you left it. A basketball does not pass through a wall. The moon does not suddenly appear in two places at once. Everyday life feels stable, solid, and predictable. That classical picture of reality is so convincing that humans naturally assume the entire universe works that way at every scale. But it doesn't. The strange thing is that quantum mechanics is not some tiny correction to physics. It is the foundation underneath chemistry, electronics, atoms, nuclear reactions, and light itself. Without quantum mechanics, modern civilization would not exist. Your phone, Wi-Fi, lasers, GPS systems, and computer chips all depend on it working correctly. So why does the world feel non-quantum? The answer is scale. Quantum effects dominate extremely small systems like electrons, photons, and atoms. But large objects interact constantly with their environment. Air molecules collide with them. Heat moves through them. Light reflects off them. Trillions upon trillions of microscopic interactions happen every second. That constant interaction destroys delicate quantum behavior almost instantly. Physicists call this decoherence. A quantum system can maintain strange combinations of possibilities only while it remains isolated from outside disturbance. Once the environment starts interacting with it, the weirdness spreads outward and effectively locks the system into stable outcomes. The larger the object, the faster this happens. That is why humans never see a cat smeared across multiple realities in daily life. A living creature interacts with its surroundings too aggressively for quantum states to survive long enough to notice. In a way, classical reality is not separate from quantum reality. It is what quantum reality looks like after enormous amounts of interaction wash out the weird behavior. Think about ocean waves from high above. From space, the ocean surface can look smooth and stable. But zoom in close enough and it becomes violent chaos full of tiny collisions and turbulence. Human experience operates at the smooth, large-scale level. Quantum mechanics rules the microscopic level underneath. Evolution also plays a role here. Human brains did not evolve to understand fundamental physics. They evolved to survive. Our senses are optimized for medium-sized objects moving at ordinary speeds on the surface of Earth. We developed intuition for throwing rocks, tracking animals, and avoiding danger, not for understanding particles behaving like probability waves. That is important because people often assume reality should match intuition. But intuition is just a survival tool shaped by biology. If humans were microscopic organisms living at atomic scales, quantum behavior might feel completely normal. We might grow up expecting objects to behave probabilistically. Deterministic physics could actually seem bizarre to us instead. Even time behaves differently depending on scale. Einstein showed that clocks change speed under gravity and motion, something completely invisible in ordinary life. Yet GPS satellites must account for those relativistic effects constantly, or navigation systems would fail within hours. Reality has never been obligated to make intuitive sense to human brains. Quantum mechanics simply pushes that mismatch to an extreme, and quantum computers expose this problem in a very direct way. These machines only function because particles retain quantum properties long enough to process information in ways impossible for classical systems. Engineers spend enormous effort shielding qubits from environmental noise because even tiny disturbances destroy the quantum states instantly. That battle against decoherence reveals something profound. The stable reality humans experience may not be the deepest layer of existence. It may be more like the visible surface produced when countless quantum interactions average themselves into something predictable. Underneath that surface, the universe appears far stranger, less definite, and far more dependent on probabilities than human intuition ever expected. At the end of the 1800s, physicists thought they were almost done. Newton's laws explained motion. Maxwell's equations explained electricity, magnetism, and light. Engineers were building industrial machines using these discoveries. The universe looked understandable, orderly, and predictable. Many scientists believed only a few small details remained unresolved. Then reality started breaking apart. The first warning sign came from something that sounded completely harmless: hot objects glowing. Physicists were studying blackbody radiation, which is the light emitted by heated objects. A stove burner glowing red, then orange, then white is an example. According to classical physics, Hotter objects should emit infinite energy at very short wavelengths. The equations predicted a catastrophic explosion of ultraviolet radiation, but nature refused to cooperate. Experimental results showed the energy output dropped off instead. The equations failed completely. In 1900, German physicist Max Planck found a desperate mathematical fix. He proposed that energy was not continuous. Instead, it came in tiny discrete packets, later called quanta. At first, Planck treated the idea almost like a mathematical trick. Even he did not fully believe nature worked that way physically, but the equations suddenly matched reality perfectly. That was the first crack. Then Albert Einstein made things worse. In 1905, Einstein explained the photoelectric effect, where light hitting metal ejects electrons. Classical wave theory predicted brighter light should gradually transfer more energy. But experiments showed something strange. Below a certain frequency, no electrons were emitted at all, regardless of brightness. Einstein proposed that light itself behaved like individual packets of energy, later called photons. This was deeply disturbing because light had already been proven to behave like a wave. Now it apparently behaved like particles too. That contradiction should not have been possible. Then came atoms. Scientists studying atomic spectra noticed atoms emitted only specific colors of light instead of continuous ranges. Hydrogen, for example, produced exact repeating spectral lines. Classical physics could not explain why electrons orbiting a nucleus did not simply radiate energy continuously and spiral inward. Niels Bohr proposed another bizarre solution. Electrons could only exist in specific allowed energy levels. They jumped between levels without occupying the space in between. Again, the math worked, but physically, it sounded insane. By the 1920s, the crisis had become unavoidable. The old model of reality was collapsing piece by piece. Physicists like Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed a completely new framework, quantum mechanics, and quantum mechanics did not behave like normal reality at all. Particles acted like waves. Waves acted like particles. Objects no longer had definite positions and speeds simultaneously. Instead, systems were described by probability waves representing possible outcomes. Even worse, measurement itself became part of the theory. In classical physics, observing a system simply revealed properties that already existed. In quantum mechanics, observation seemed tied directly to what outcome became physically real. Einstein hated this conclusion. He famously argued that God does not play dice. He believed the probabilistic nature of quantum mechanics had to be temporary ignorance hiding a deeper deterministic reality underneath. But every decade strengthened quantum theory instead. The equations predicted atomic behavior with terrifying accuracy. Chemistry worked because of quantum mechanics. Semiconductor physics worked because of quantum mechanics. Nuclear physics worked because of quantum mechanics. The theory became the most successful scientific framework ever created. And that success created a strange problem. Physicists could use the equations perfectly while still arguing endlessly about what the equations actually meant. Even today, scientists disagree on the deeper interpretation of quantum mechanics. Was reality fundamentally probabilistic? Did measurement create outcomes? Were multiple realities branching constantly? Or was some hidden layer still undiscovered? Quantum computers now sit directly in the middle of that debate, because these machines are not just using quantum equations abstractly, they rely on the weirdness physically existing in nature. That means the crisis that began in the early 1900s never truly ended. Humanity simply learned how to build technology on top of it. If there is one experiment that captures everything disturbing about quantum mechanics, it is the double-slit experiment. It looks simple enough that you could explain it to a child. Imagine a wall with two narrow slits cut into it. Behind the wall is a screen that records where incoming particles land. If you fire tiny objects like BB pellets through the slits, you expect two clusters to appear on the screen, one behind each opening. That is exactly what happens. Now replace the BB pellets with waves. Waves behave differently. When water waves pass through two gaps, the ripples spread out and overlap. Some regions reinforce each other, while others cancel out. The result is an interference pattern, alternating bright and dark bands. Light creates that exact wave interference pattern too. So far, Nothing strange, but then physicists started firing individual particles instead of continuous waves. Single electrons, one at a time. And reality stopped making sense. Even when electrons were fired individually with long delays between them, the interference pattern still appeared gradually on the screen. Somehow each electron behaved like a wave passing through both slits simultaneously and interfering with itself. That alone was already bizarre. But the truly disturbing part came next. Scientists placed detectors near the slits to observe which path the electron actually took. The moment they measured the path, the interference pattern disappeared. The electron suddenly behaved like a normal particle again, passing through one slit or the other. Observation changed the outcome, not because the scientists physically touched the electron in some obvious mechanical way. The very act of obtaining path information altered the result. This experiment has been repeated in countless forms for decades, using electrons, photons, atoms, and even large molecules. The outcome never changes. Without measurement, quantum systems evolve like overlapping possibilities. With measurement, one outcome becomes definite. Nobody fully agrees on what that means. One interpretation says the wave function physically collapses during measurement. Another says the observer becomes entangled with the system. Another says all possible outcomes continue existing in separate branches of reality. Yet another claims particles always possess definite positions guided by hidden quantum waves. The equations predict the same results either way. But philosophically, these interpretations describe completely different universes. Richard Feynman, one of the greatest physicists in history, openly admitted the double-slit experiment contains the central mystery of quantum mechanics. He once said nobody truly understands it. And that was before quantum computers existed. Because now this strange behavior is no longer confined to isolated lab demonstrations. Quantum processors depend directly on superposition and interference to perform calculations. Engineers are effectively building controlled versions of the double-slit experiment inside computing hardware. A qubit works because quantum states can overlap like waves. Different computational paths interfere with each other mathematically, strengthening correct answers while cancelling wrong ones. If observation or environmental noise destroys the quantum state too early, the computation collapses. In other words, quantum computers only work because nature really does behave this strangely. That is what makes the double-slit experiment so unsettling even today. It is not merely an abstract puzzle from physics textbooks anymore. It appears to reveal something fundamental about how reality processes information. The universe, at microscopic scales, does not behave like a collection of tiny solid objects moving along definite paths. Instead, it behaves more like a system of evolving probabilities that become concrete only during interaction. And the hardest part to accept is that this is not fringe science. The predictions are accurate to astonishing precision. Quantum mechanics has passed every serious experimental challenge ever thrown at it. The equations work almost perfectly. Humans are the part struggling to keep up. Because the double-slit experiment forces a possibility that feels almost impossible to accept intuitively. Before measurement, reality may not be fully decided in the ordinary sense at all. For most of computing history, engineers treated quantum mechanics like a problem. As computer chips became smaller and more powerful, quantum effects started interfering with normal electronics. Electrons tunneled through barriers they were not supposed to cross. Tiny fluctuations created instability. Heat and atomic scale randomness became serious engineering obstacles. The entire goal of classical computing was stability. A bit had to remain clearly defined as either a 0 or a 1. No ambiguity, no probability. Reliable machines require predictable states. Quantum computing completely flips that idea upside down. Instead of suppressing quantum behavior, these machines depend on it. A normal computer bit works like a light switch. Off means 0. On means 1. Every calculation inside your laptop ultimately reduces to enormous combinations of those definite states. A qubit behaves differently because it follows quantum rules. Instead of existing strictly as 0 or 1, it can exist in a superposition of both simultaneously. That word, superposition, often gets oversimplified, but the core idea is important. A qubit is not secretly choosing one value while hiding it from us. Its state genuinely behaves like overlapping possibilities that evolve together mathematically until measurement produces a final outcome. That sounds impossible because human intuition expects reality to contain definite answers at all times. Quantum mechanics disagrees, and quantum computers only work if quantum mechanics is telling the truth. This is where things become deeply strange. When multiple qubits become entangled, their possible states combine into an enormous probability structure. A system with just a few hundred qubits can mathematically represent more possible configurations than there are atoms in the observable universe. That does not mean quantum computers literally try every answer in parallel universes the way science fiction often describes it. The real process is more subtle. Quantum algorithms manipulate interference patterns among probabilities. Correct solutions become amplified while incorrect ones cancel out. It is less like brute force guessing and more like shaping waves. One useful analogy is noise-cancelling headphones. Those headphones remove unwanted sound by creating interference patterns that cancel certain frequencies. Quantum algorithms use similar principles mathematically. They arrange probability waves so unwanted outcomes interfere destructively while useful outcomes survive. But maintaining these quantum states is unbelievably difficult. The moment a qubit interacts too strongly with its environment, decoherence occurs. The quantum information leaks outward into the surroundings, and the delicate superposition collapses into an ordinary classical state. Heat, vibrations, radiation, or even tiny electromagnetic disturbances can destroy calculations instantly. That is why quantum computers often look so bizarre physically. Many operate near absolute zero inside massive refrigeration systems, colder than outer space. Engineers are trying to isolate qubits from reality itself long enough for computations to survive, and that effort reveals something important. Quantum mechanics is not just a mathematical trick scientists use to describe experiments. Quantum computers demonstrate that the strange probabilistic structure appears physically real enough to engineer around. If particles secretly possessed ordinary hidden states underneath quantum mechanics, many of these computational advantages should disappear. Classical systems simply cannot reproduce the same interference behavior efficiently at scale. That is why recent experiments verifying genuine entanglement inside quantum processors cause such attention. Researchers are increasingly confident these machines are exploiting authentic, non-classical phenomena rather than clever simulations. In simple terms, humanity may now be building technology directly on top of the fact that reality itself is fundamentally weird. And the implications go beyond computing power. Quantum computers force people to confront an uncomfortable possibility. The universe at its deepest level may not operate like a fixed machine evolving through definite states. Instead, reality may behave more like a constantly evolving web of probabilities, interactions, and information relationships that only appear stable once large-scale decoherence hides the underlying uncertainty. That idea sounds philosophical, but now it is sitting inside laboratories as working hardware. For years, critics of quantum computing had a reasonable argument. Yes, quantum mechanics predicts strange behavior. Yes, laboratory experiments repeatedly confirm those predictions. But maybe quantum computers were not truly using deep quantum effects the way researchers claimed. Maybe the machines only looked quantum because of clever engineering tricks or incomplete measurements. That skepticism became harder to maintain after a series of verification experiments designed to answer a very direct question. Are quantum processors genuinely exploiting non-classical physics, or are they effectively faking it? Some researchers jokingly describe these tests as quantum lie detectors. The challenge was more difficult than it sounds. Quantum systems are incredibly fragile, noisy, and difficult to measure without disturbing them. Early quantum computers were small enough that classical supercomputers could simulate their behavior well enough to check the answers manually. But as quantum processors grew larger, classical verification became nearly impossible. A sufficiently powerful quantum system produces probability spaces so enormous that ordinary computers cannot efficiently track all possible states. That created an awkward problem. How do you prove a machine is performing genuinely quantum operations if the calculations themselves become too complex for classical systems to verify directly? Researchers developed new methods based on statistical correlations, entanglement structure, and Bell-type tests. Instead of checking every internal calculation step by step, scientists examined whether the machine produced patterns impossible for classical systems to reproduce efficiently. And this is where things became philosophically explosive. The results strongly suggested the processes were not simply imitating quantum mechanics. The entanglement correlations matched predictions that violate classical assumptions about local hidden variables. That phrase sounds technical, but the implication is huge. A hidden variable theory assumes particles already contain definite instructions determining future outcomes before measurement occurs. Einstein preferred this kind of explanation because it preserved a stable objective reality underneath quantum uncertainty. But Bell's theorem, proposed in the 1960s, showed something remarkable. If local hidden variables exist, certain statistical relationships must always hold during measurements of entangled particles. Quantum mechanics predicts violations of those limits, and experiments consistently observe those violations. Modern quantum processors are now reproducing these effects inside functioning computational systems rather than isolated physics demonstrations. The machines appear to depend directly on genuinely non-classical entanglement. In other words, the weirdness is not staying trapped inside abstract equations anymore. Engineers are building hardware around it. This matters because it removes one of the last comforting escape routes. For decades, people could imagine quantum mechanics as incomplete bookkeeping hiding a more intuitive reality underneath. But every successful Bell test narrows the room for that possibility. Nature keeps behaving as though particles do not possess fully independent predetermined properties before interaction. Something about reality itself appears relational, and quantum computers are making that impossible to ignore. One reason this unsettles people so deeply is because classical thinking is built into human psychology. We instinctively assume objects possess fixed attributes whether observed or not. A baseball has a location. A coin already landed heads or tails before you uncover it. Reality feels definite. Quantum experiments keep suggesting microscopic reality does not operate that way. Instead, measurable properties may only emerge through interactions between systems. That does not mean human consciousness magically creates the universe. Most physicists reject that interpretation. A detector, an atom, or even environmental interaction can produce measurement effects without any conscious observer involved. But it still means the universe may not contain fully settled physical facts independent of interaction in the classical sense people imagine. That is the real source of discomfort. Quantum computers are not terrifying because they might become intelligent. They are terrifying because they function at all. Every successful quantum operation reinforces the possibility that the underlying fabric of reality is fundamentally probabilistic, interconnected, and resistant to the idea of a detached objective world existing independently of measurement relationships. And the more powerful these machines become, the harder that conclusion becomes to avoid. Out of all the strange ideas in quantum mechanics, entanglement may be the one that disturbed Einstein the most, because unlike the double-slit experiment, entanglement does not just challenge intuition about particles, it challenges the structure of reality itself. The basic setup sounds simple. Two particles interact in a way that links their quantum states together. After that interaction, the particles can become entangled, meaning their properties are no longer fully separate descriptions. Instead, the system has to be treated as one combined quantum state, even if the particles later move very far apart. Imagine creating two entangled particles and sending one to Earth and the other to the Moon. According to quantum mechanics, measuring one particle instantly affects what can be predicted about the other. Not after a delay, instantly. Einstein hated this idea because it appeared to violate one of the deepest principles in physics, locality. Locality says objects should only be influenced by their immediate surroundings. Information should not travel faster than light. Nothing happening on Earth should instantly affect something on the Moon. Einstein believed quantum mechanics had to be incomplete. He argued the particles probably carried hidden information from the start, like two gloves packed separately in boxes. Open one box and see a left glove, and you instantly know the other contains the right glove. No spooky communication required. For a while, that explanation sounded reasonable. Then physicist John Bell changed everything. In 1964, Bell developed a mathematical theorem that allowed scientists to experimentally test whether hidden variables could explain entanglement. His equations showed something extraordinary. If particles contain predetermined local properties, certain statistical limits must always hold. Quantum mechanics predicted violations of those limits. That meant experiments could finally distinguish between Einstein's intuition and the quantum framework. Over the following decades, researchers repeatedly performed Bell tests using entangled photons, electrons, and other particles. Again and again, the results matched quantum mechanics. The Bell inequalities were violated. Einstein's local hidden variable picture kept failing. Modern experiments have become even more convincing. Physicists closed loopholes involving detector efficiency, timing coordination, and information leakage. Some tests separated measurements by kilometers, while ensuring signals moving at light speed could not coordinate outcomes in time. The violations still appeared. Something fundamental had to give way. Either locality fails, meaning distant events can be connected in ways classical physics never expected, or realism fails, meaning particles do not possess definite properties prior to measurement. Some interpretations sacrifice locality. Others sacrifice realism. A few attempt to rethink both entirely. But almost nobody working seriously in physics today believes the universe behaves like a simple classical machine underneath quantum mechanics. And quantum computers rely directly on this phenomenon. Entanglement is not just a philosophical curiosity sitting in textbooks. It is one of the main resources quantum processors use to outperform classical systems. Multiple qubits become linked in ways impossible for ordinary bits. Their combined states evolve together as a unified probability structure. Without entanglement, most quantum computational advantages disappear. That means every functioning quantum processor acts as another practical demonstration that reality permits these bizarre, non-classical relationships. And this is where people start feeling genuinely uncomfortable, because entanglement suggests the universe may not be built from separate, independent objects the way humans naturally imagine. At deep levels, systems appear fundamentally interconnected. The properties of one object can become inseparable from the properties of another, even across enormous distances. Reality begins looking less like isolated things moving through empty space and more like one giant relational structure. This does not mean faster-than-light communication is possible. Quantum entanglement cannot transmit usable messages instantly. Relativity still survives, but the correlations themselves remain deeply strange. Even physicists who work with entanglement professionally often admit it feels unnatural. And the strangest part is that quantum computers are now transforming this once purely philosophical problem into engineering reality. Humanity is no longer just observing spooky action at a distance. We are learning how to program it. At this point, the obvious question starts forming. If quantum particles behave like unresolved probabilities before measurement, then what exactly is reality doing before interaction happens? This is where quantum mechanics stops feeling like strange physics and starts feeling psychologically disturbing. In classical thinking, the world exists in a fully defined state whether anyone looks at it or not. A book on a table has a precise position, color, and orientation at every moment. Human observation simply reveals those properties. Quantum mechanics challenges that assumption at a fundamental level. According to the mathematical framework, particles are described by wave functions containing multiple possible outcomes simultaneously. The wave evolves smoothly through time until interaction occurs. Then, one measurable outcome appears. The problem is that physicists still argue over what this process actually means. One interpretation says the wave function represents real physical possibilities that genuinely coexist before measurement. Another says the wave only reflects human knowledge and probabilities update when information changes. Others claim every outcome happens in branching realities. But nearly all interpretations agree on one uncomfortable fact. Quantum systems do not behave as though they contain fully settled classical properties before interaction. That distinction matters. Popular science headlines often oversimplify this idea into "consciousness creates reality." That is not what mainstream physics says. Human awareness is not required. A photon hitting a detector counts as interaction. Molecules colliding with airs count as interaction. Even environmental noise can force quantum systems into stable states. The key idea is not human observation. It is interaction itself. And that changes the picture of reality dramatically. Instead of imagining the universe as a giant machine with predefined properties everywhere at all times, quantum mechanics suggests measurable facts may emerge through relationships between systems. Some physicists describe this as relational reality. Properties are not necessarily absolute independent things. They arise through interactions. That sounds abstract until you apply it to ordinary assumptions. Take position. In classical physics, an object simply has a location. In quantum mechanics, position behaves probabilistically until measured relative to another system. The same applies to momentum, spin, polarization, and many other properties. At large scales, decoherence hides this uncertainty so effectively that the world appears stable and objective. But beneath that classical surface, quantum systems continue evolving according to probabilities rather than definite trajectories. Quantum computers are important here because they are engineered attempts to preserve that unresolved quantum behavior long enough to perform useful tasks. The qubits inside these systems exist in carefully controlled superpositions. Engineers fight constantly against unwanted environmental interactions because once outside disturbances occur, the quantum information collapses into ordinary classical outcomes. In other words, the computation depends directly on keeping reality partially unresolved. That sentence sounds almost absurd, yet it describes the engineering challenge accurately. And this is where the horrifying interpretation enters. If quantum mechanics truly reflects the structure of nature, then the definite world humans experience may not be fundamental. Stability could emerge only after massive layers of interaction and decoherence force probabilities into consistent, large-scale outcomes. The universe underneath might be less like a completed physical scene and more like a network of evolving potential relationships. That idea deeply conflicts with human intuition, because our brains evolve to perceive certainty and persistence. We experience a continuous, stable environment because survival depends on it, but evolution never promised humans an accurate perception of fundamental reality. Quantum mechanics keeps revealing that nature operates according to rules that feel alien compared to ordinary experience, and quantum computers are making those rules impossible to dismiss as purely philosophical speculation. These machines function because unresolved quantum possibilities can remain physically meaningful long enough to manipulate information. That means the deepest layer of reality may not consist of fixed objects carrying definite properties through time. Instead, measurable reality itself may emerge through interaction. Most quantum thought experiments are strange. Wigner's friend is different. It feels almost dangerous to think about for too long because it attacks one of the deepest assumptions humans rely on every day, that there is one objective reality everyone shares. The thought experiment was proposed by physicist Eugene Wigner in the 1960s as an extension of the measurement problem in quantum mechanics. Here's the setup. Imagine a scientist inside a sealed laboratory performing a quantum measurement. The scientist measures a particle that exists in a superposition of possible states. From the scientist's perspective, inside the lab, the measurement produces a definite result. The particle becomes one outcome or the other. Simple enough. But now imagine an outside observer looking at the entire laboratory from the outside. According to quantum mechanics, if the outer observer has not interacted with the lab yet, the entire room could still mathematically behave like a superposition. Not just the particle, but the scientist, the measurement device, and the recorded outcome all become part of one larger unresolved quantum system. That creates a terrifying contradiction. Inside the lab, the scientist sees one definite reality. Outside the lab, the observer may describe the entire system as multiple possibilities existing simultaneously. So which description is correct? Quantum mechanics appears to allow both, and that is where objective reality starts breaking apart. In classical physics, this problem would never happen because measurements simply reveal pre-existing facts. Once the particle is measured, everyone should agree on the outcome, whether they looked yet or not. Quantum mechanics complicates that picture because the theory treats observers and measuring devices as physical systems too. If quantum rules apply universally, then even observations themselves can become entangled. For decades, Wigner's friend remained mostly philosophical because testing such ideas experimentally seemed impossible. You would need to place increasingly complex systems into quantum superpositions while preserving coherence long enough to compare observer perspectives. Modern quantum technologies are changing that. Researchers have now performed simplified experimental versions inspired by Wigner's friend scenarios, using entangled photons and quantum information systems. These experiments do not literally place conscious humans into superpositions, despite sensational headlines. But they do recreate the logical structure of conflicting observations. And the results are deeply uncomfortable. Some experiments suggest different observers can record internally consistent but incompatible facts about the same quantum event. That does not necessarily mean reality is subjective in the everyday sense people imagine. You cannot simply invent your own universe mentally, but it does suggest the concept of one absolute observer-independent set of facts may not function cleanly at quantum scales. Some physicists respond by saying quantum states are relative to observers. Others argue branching realities solve the contradiction because every outcome exists separately. Others insist decoherence prevents these paradoxes from mattering macroscopically, but nobody fully agrees. And quantum computing keeps pushing these questions from philosophy toward engineering reality. Quantum processors manipulate entangled systems containing increasingly large collections of qubits. As these systems scale, researchers are forced to confront deeper questions about measurement, information, and observer relationships. What counts as an observation? When exactly does a quantum outcome become definite? Can facts exist relative to one system, but unresolved relative to another? These are no longer purely abstract discussions. The horrifying part is not that quantum mechanics proves reality is fake. It is that the theory appears surprisingly comfortable with ambiguity in places humans expect certainty. Our brains assume truth should work like a stable photograph. One event happens. Everyone agrees on it. Reality moves forward objectively from there. Quantum mechanics may not operate that way fundamentally. At microscopic scales, different observers can apparently describe the same process differently, while both remaining mathematically correct within their own frame of interaction. And if that sounds impossible, that's because human intuition evolved in a classical world where decoherence hides these contradictions almost perfectly. Quantum computers are beginning to expose the cracks underneath that illusion. At some point, physicists faced a brutal choice. Quantum mechanics worked perfectly mathematically, but nobody could explain what actually happens during measurement without running into contradictions. The equations describe multiple possible outcomes evolving together smoothly over time, but observation seems to produce one definite reality. So where do the other possibilities go? The traditional Copenhagen interpretation basically says the wave function collapses during measurement. Before observation, probabilities exist. After measurement, one outcome becomes real. But some physicists hated this idea because the collapse itself is strangely undefined. What counts as a measurement? Why should observation suddenly change the rules? At what exact moment does possibility become reality? In 1957, physicist Hugh Everett proposed a radical alternative. Maybe the wave function never collapses at all. Instead, every possible outcome continues existing in separate branches of reality. This became known as the many worlds interpretation. According to this idea, quantum mechanics is mathematically complete exactly as written. The universe simply evolves into multiple versions whenever quantum events produce different outcomes. Imagine flipping a quantum coin. In one branch, it lands heads. In another branch, it lands tails. Both outcomes happen, but observers inside each branch only experience one version. That sounds completely insane at first. Even many physicists initially dismissed it as science fiction disguised as mathematics. But over time, some researchers began taking the interpretation more seriously because it solves certain problems cleanly. There is no mysterious collapse, no special role for observers, no sudden transition from quantum uncertainty into classical certainty. The wave function simply evolves continuously according to the equations. The price is accepting an unimaginably vast number of branching realities, and this is where quantum computing enters the conversation. Some supporters of many worlds argue quantum computers make the interpretation feel more plausible. Their reasoning is controversial, but fascinating. Quantum algorithms manipulate huge combinations of possible states simultaneously. Certain computations appear exponentially difficult for classical systems because the number of possibilities grows explosively. Yet, quantum computers can process these probability structures efficiently through interference effects. Physicist David Deutsch famously suggested this behavior makes the most sense if quantum computations are distributed across many branches of reality interacting mathematically. To be clear, this does not mean quantum computers are literally opening portals to alternate universes. That oversimplification spreads constantly online and is not how mainstream physics describes the machines. But the deeper philosophical point remains unsettling. Quantum computers behave as though multiple possible computational paths coexist and interfere before one measurable result emerges. Many worlds says all those paths are physically real. Most physicists remain cautious here because the interpretation cannot currently be tested directly against competing interpretations. Copenhagen, many worlds, relational quantum mechanics, and several other frameworks all reproduce the same experimental predictions. That means the debate becomes philosophical as much as scientific. Still, many worlds refuses to disappear because it removes the need for collapse entirely. The equations already describe evolving superpositions naturally. Everett's interpretation simply takes the mathematics seriously all the way down, and the consequences become deeply uncomfortable. If many worlds is correct, then every quantum event continuously branches reality into countless versions. Tiny microscopic uncertainties spread outward through decoherence until entire macroscopic histories diverge. Different outcomes of accidents, different biological mutations, different human decisions influenced indirectly by quantum randomness, different futures constantly unfolding. You would only ever experience one branch, creating the illusion of a single stable timeline. Quantum computers intensify these discussions because they force scientists to manipulate large, coherent quantum systems directly. The machines operate in ways that look increasingly difficult to reconcile with classical single-outcome intuitions. Again, this does not prove many worlds is true, but it keeps the interpretation alive, and that may be the most unsettling part of all. The equations underlying modern technology are compatible with a picture of reality where unimaginably many versions of events coexist simultaneously, while conscious observers experience only one thin slice moving through the branching structure. Not because science fiction invented it, because the math never ruled it out. The reason many worlds unsettles people so deeply is not just because it suggests multiple realities exist. It is because of what that idea implies about your own life. In everyday experience, humans feel like they move through one continuous timeline. The past happened one way, the future has not happened yet. Choices lead to outcomes, and reality follows a single path forward. Many worlds destroys that picture completely. If the interpretation is correct, quantum events never collapse into one final outcome. Instead, every possible result continues existing in separate branches of reality. At microscopic scales, quantum uncertainty constantly exists everywhere, inside atoms, photons, chemical reactions, and possibly even some biological processes. Most of those quantum events are tiny, but through decoherence, their effects spread outward into larger systems. That means reality could be branching continuously. Not occasionally, constantly. In one branch, a particle decays now. In another, it decays later. In one branch, a neuron fires slightly differently. In another, it does not. Tiny differences grow over time until entirely different histories emerge. The horrifying part is that every branch contains observers who believe their reality is the one true continuation, including you. Imagine walking across a street while a car approaches. In one branch, the driver brakes successfully. In another, they do not. In one branch, you survive an illness. In another, you never recover. Different outcomes continue separately, each containing versions of people experiencing those realities as completely normal. From your perspective, you only ever experience one branch unfolding. You never feel the split happen. That idea creates an eerie sense that countless alternative histories may exist beyond the version you currently inhabit, completely inaccessible yet mathematically connected through the same quantum framework. Again, this is interpretation, not experimentally proven fact. Many worlds is one way physicists attempt to explain quantum mechanics without collapse. Other interpretations avoid branching realities entirely, but what makes many worlds hard to dismiss emotionally is how naturally it follows from the equations themselves. The Schrödinger equation evolves smoothly and continuously. Nothing inside the mathematics explicitly says probabilities must disappear into one outcome. Collapse has to be added separately. Everett's interpretation simply refuses to add it. Quantum computers make this discussion feel less abstract because they manipulate overlapping computational possibilities directly. During calculations, qubits evolve through enormous combinations of states before interference selects measurable outcomes. Supporters of many worlds argue this process resembles branches interacting mathematically before decoherence isolates them. Most physicists avoid making such dramatic claims publicly because the interpretation remains untestable for now. But the philosophical tension remains impossible to ignore, and there is another deeply unsettling implication. If branching realities exist, then personal identity becomes harder to define cleanly. Which future version is really you? Suppose reality branches after a quantum event influences your life. Both resulting versions remember being the same person up to that point. Both feel continuous. Both believe they are the authentic continuation. From inside each branch, the split becomes invisible immediately afterward. That challenges the ordinary human idea of a singular self moving through time. The deeper people think about many worlds, the stranger existence starts to feel. Reality stops resembling a single unfolding story and starts resembling an unimaginably vast structure containing countless parallel histories evolving simultaneously. And yet you experience only one thread. Not because the others are unreal, according to this interpretation, but because decoherence isolates branches so completely they effectively stop interacting. Quantum mechanics never promised the universe would feel emotionally comfortable. It only promised accurate predictions. And that may be why quantum computing unsettles people beyond normal technological fear. These machines are forcing society to engage with interpretations of reality that sound more like existential philosophy than engineering. But underneath the speculation sits an uncomfortable truth. The equations powering modern quantum technology do not require reality to follow a single, definite path at all. At this point, a reasonable person usually asks the same question. If the universe is truly this strange, why does everyday reality feel so normal? Why do people not see objects existing in multiple states? Why are cats not smeared across probabilities? Why does the world appear solid, stable, and objective if quantum mechanics sits underneath everything? The answer is one of the most important ideas in modern physics: decoherence. Decoherence is what happens when a quantum system interacts with its environment and loses its delicate quantum behavior. The interaction spreads quantum information outward into surrounding particles, effectively destroying the coherent superpositions needed for quantum effects to remain visible. In simpler terms, reality becomes classical because the environment constantly forces quantum possibilities to settle into stable outcomes. Imagine trying to hear a whisper during a hurricane. The signal gets drowned instantly by noise. Quantum states behave similarly, and tiny isolated systems can maintain superpositions briefly, but once they interact with trillions of surrounding particles, the fragile quantum relationships disappear almost immediately. This process happens unbelievably fast for large objects. An isolated electron can maintain quantum coherence relatively easily under controlled laboratory conditions. A dust particle loses coherence almost instantly. A human being filled with heat, molecular motion, light interactions, and constant environmental contact decoheres so aggressively that quantum superpositions become effectively impossible to observe directly. That is why humans experience a stable classical world. Not because quantum mechanics stops applying at large scales, but because decoherence hides the underlying quantum structure so efficiently that only one consistent macroscopic outcome remains visible. This idea changed physics profoundly because it helped explain why the world appears classical without requiring a magical boundary between quantum and non-quantum reality. There is no clear dividing line. The same quantum rules apply everywhere, but complexity and environmental interaction wash out the weirdness. Quantum computers reveal this process very clearly because engineers spend enormous effort fighting decoherence constantly. Qubits must remain isolated enough to preserve superpositions during calculations. Even tiny disturbances from heat, electromagnetic radiation, vibrations, or nearby atoms can collapse the quantum state prematurely. That is why many quantum processors operate inside giant dilution refrigerators cooled to temperatures colder than deep space. Engineers are trying to suppress environmental interaction long enough for coherent quantum behavior to survive. In a sense, quantum computers are machines built to temporarily resist ordinary reality. And the fact that this works at all is remarkable. The systems remain fragile because decoherence is relentless. Every interaction with the outside world leaks information outward. Once enough information spreads into the environment, the quantum behavior effectively disappears from observation. This also explains why many world supporters connect decoherence to branching realities. In that interpretation, decoherence does not destroy alternate possibilities. It simply prevents different branches from interfering with each other anymore. Each branch becomes effectively isolated, creating the appearance of one stable classical outcome from inside each observer's perspective. Other interpretations explain decoherence differently, but nearly all agree on its practical importance. Without decoherence, reality would not look stable. Atoms might not hold together consistently. Chemistry would behave unpredictably. Large-scale structures could not maintain definite classical properties long enough for life to function normally. The world humans evolved inside depends on decoherence constantly filtering quantum uncertainty into stable, large-scale behavior. And that creates a strange philosophical realization. What people call reality may actually be a simplified surface layer emerging from deeper probabilistic processes underneath. Classical certainty could be less fundamental than quantum possibility. Human intuition struggles with this because our brains evolved entirely within the decohered layer. We naturally assume stability, definiteness, and object permanence because those assumptions work perfectly at human scales. But quantum physics keeps suggesting the deeper universe operates very differently, and quantum computers are important because they expose that hidden layer directly. They function only by preserving forms of quantum behavior that ordinary reality normally suppresses almost instantly. In other words, these machines are forcing humanity to interact with parts of nature our senses were never designed to perceive. For decades, the deepest questions in quantum mechanics were treated almost like philosophical side discussions. Physicists focused on calculations instead. That attitude became famous through a phrase often associated with quantum theory: shut up and calculate. The idea was simple. Quantum mechanics predicts experiments with extraordinary accuracy, so arguing endlessly about what the equations really mean was seen by many researchers as unnecessary. And honestly, that approach worked. Quantum theory helped create transistors, lasers, MRI machines, semiconductors, nuclear technology, and modern electronics. Engineers could build world-changing devices without solving the philosophical mysteries underneath. But quantum computing is changing that situation. Because now scientists are no longer just applying quantum equations to tiny particles inside isolated laboratory experiments. They are trying to control large entangled systems, preserve coherence across many qubits, and manipulate reality at scales where the interpretation questions become harder to ignore. The engineering itself keeps running into foundational physics. Take measurement, for example. In ordinary quantum experiments, measurement marks the transition from delicate superposition into definite outcomes. But quantum computers constantly dance near that boundary. Engineers need qubits isolated enough to remain quantum during calculations, yet measurable enough to extract useful answers at the end. That creates practical questions with philosophical consequences. What exactly counts as a measurement? How does information leakage destroy coherence? At what point does environmental interaction force classical outcomes? These are not abstract metaphysical debates anymore. They directly affect whether quantum processes function. Researchers are also pushing quantum systems into scales that once seemed impossible. Early experiments involved single particles or simple entangled pairs. Modern quantum processors can contain hundreds or even thousands of interacting qubits, depending on architecture and error correction methods. As these systems grow, physicists gain new tools for testing reality itself. Some scientists now use quantum computers and quantum simulators to study exotic phases of matter, black hole information behavior, space-time geometry, and entanglement structure. In some cases, quantum systems can model physical processes that classical computers struggle to simulate accurately. That means quantum technology is becoming both a computational tool and an experimental window into foundational physics. And the results keep reinforcing the same uncomfortable message. The universe does not appear fundamentally classical underneath. Entanglement remains real. Probabilities remain fundamental. Observer-independent hidden variable explanations keep running into experimental trouble. Even reality itself starts looking increasingly tied to information relationships rather than fixed material states. This shift is changing the culture of physics, slowly but noticeably. Younger researchers today are often more willing to discuss interpretations openly because quantum information theory has made foundational questions useful again. Concepts once dismissed as philosophical distractions now connect directly to practical research in computing, cryptography, thermodynamics, and quantum gravity. For example, entanglement is no longer just a weird prediction in textbooks. It is treated as a measurable resource that can be quantified, manipulated, and engineered. Information itself is increasingly viewed as a physical quantity rather than merely an abstract bookkeeping tool. That evolution matters because it blurs the boundary between philosophy and physics. Questions about what reality actually is are slowly moving back toward mainstream scientific discussion. Not because physicists suddenly became mystical, but because modern experiments keep forcing the issue. Quantum computing especially accelerates this process because the technology works only by exploiting features of nature that classical intuition says should not exist. Every successful quantum algorithm becomes another reminder that the microscopic world does not obey ordinary assumptions about separateness, definiteness, or deterministic certainty. And perhaps the strangest part is this. The more advanced quantum technology becomes, the less human intuition seems trustworthy. Classical reality may simply be the simplified approximation humans evolved to survive within, while the deeper structure underneath operates according to principles far stranger than common sense ever expected. Quantum computers are not creating those mysteries, they are exposing how long they were already there. One of the strangest shifts in modern physics is that information no longer looks like just an abstract human concept. Increasingly, physicists treat information as something physically real. That sounds harmless at first, but it leads to unsettling consequences very quickly. In everyday life, people think of information as symbolic. A text message, a password, a book, or a computer file all contain information, but the information itself seems separate from physical reality. It feels like meaning layered on top of matter. Physics is starting to blur that distinction. A major turning point came from black holes. According to general relativity, a black hole forms when enough mass collapses into a small region of space. Gravity becomes so intense that not even light can escape beyond the event horizon. For a while, black holes looked simple from the outside. They appeared to erase details about whatever fell into them. Then Stephen Hawking made the situation far stranger. In the 1970s, Hawking showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly emit radiation and eventually evaporate over enormous timescales. That created a massive problem. If a black hole evaporates completely, what happens to the information about everything that fell inside? Quantum mechanics says information cannot simply vanish. The evolution of quantum systems preserves information mathematically. But Hawking's calculations seem to suggest black holes could permanently destroy it. This became known as the black hole information paradox, and physicists took it extremely seriously because it hinted at a conflict between quantum mechanics and gravity, the two greatest theories in modern science. Over time, many researchers came to believe the information must somehow survive. But the deeper implication was shocking. Information might be more fundamental than space-time itself. Some theories now suggest the geometry of space could emerge from patterns of quantum entanglement. In certain models of quantum, gravity space-time behaves less like a fixed stage and more like a structure built from information relationships underneath. That idea would have sounded insane a century ago. Now it appears in serious theoretical research. Quantum computing plays directly into this shift because quantum information behaves differently from classical information. Entangled systems store correlations across particles in ways ordinary physics never anticipated. Quantum teleportation, error correction, and entanglement entropy all suggest information has deep physical structure. In fact, many physicists now define reality operationally through information exchange. What can be measured? What correlations exist? What information becomes accessible between systems? Those questions increasingly sit at the center of modern physics. And this changes the way people think about matter itself. Instead of imagining tiny billiard ball particles carrying definite properties through space, Quantum theory often describes systems through states, probabilities, and informational relationships. Physical reality starts looking less like solid objects and more like evolving patterns of interaction. That does not mean the universe is literally a computer simulation, despite what online discussions often claim. Most physicists reject simplistic simulation theory arguments because they usually misunderstand how information works in physics. But the shift remains profound. The universe may not fundamentally consist of material objects sitting inside empty space. Matter, energy, space, and time themselves might emerge from deeper informational structures. Quantum computers make this idea feel more concrete because they manipulate information at the deepest quantum level. Qubits are not merely tiny switches. Their states encode probability amplitudes, interference relationships, and entanglement structures that classical systems cannot replicate efficiently. The power of these machines comes from the physics of information itself, and that creates an unsettling possibility. Reality may care less about solid objects than humans naturally assume. At the deepest level, the universe might be built more from relationships, probabilities, and informational structure than from stable, independent things. Human intuition resists that idea because people evolved to perceive objects, surfaces, and definite events. But modern physics keeps pointing beneath that familiar layer towards something much stranger. A universe where information is not just something reality contains, but something reality may actually be made from. For most of human history, space and time felt like the most basic parts of reality. Everything exists somewhere. Everything happens sometime. Even Isaac Newton treated space and time as fixed universal backgrounds where physical events unfold. Einstein later reshaped that picture through relativity, showing space and time are flexible, connected, and affected by gravity. Massive objects bend space-time itself. But modern physics may be pushing things even further. Some researchers now suspect space and time are not fundamental at all. Instead, they could emerge from deeper quantum processes underneath. This idea sounds almost impossible because humans experience space-time directly every moment of their lives. Distance feels real. Time feels like a continuous flow. The entire structure of human perception depends on navigating space and remembering events through time. Yet several major problems in physics hint that space-time may break down at deeper levels. The biggest issue is the conflict between general relativity and quantum mechanics. General relativity describes gravity and large-scale space-time beautifully. Quantum mechanics describes microscopic reality with incredible precision. But when scientists try combining them under extreme conditions like inside black holes or near the Big Bang, the equations become unstable and contradictory. Something fundamental appears incomplete. One possibility is that space-time itself is not the true foundation. Instead, space and time may emerge from quantum relationships the way temperature emerges from atomic motion. A single atom does not possess temperature alone. Temperature appears collectively when enormous numbers of particles interact statistically. Some physicists suspect space-time works similarly. Distance, geometry, and even causality could emerge from deeper quantum structures, involving entanglement and information. This idea gained attention partly because of discoveries involving black holes and holographic principles. Certain theories suggest the information describing a region of space may actually live on lower dimensional boundaries surrounding it, almost like a hologram generating a three-dimensional image. That sounds bizarre, but the mathematics connecting gravity, quantum mechanics, and information theory keeps pointing in similar directions. Entanglement appears especially important. Some researchers now believe quantum entanglement may literally help stitch space-time together. In certain theoretical models, changing entanglement patterns alters the geometry of space itself. Remove enough entanglement and space-time could effectively fall apart. In this picture, the universe stops looking like objects moving through pre-existing space. Instead, space itself becomes a product of quantum connections. Quantum computing enters this conversation because quantum information systems allow scientists to study entanglement structure much more deeply than before. Some researchers use quantum circuits and tensor networks to simulate simplified versions of space-time behavior mathematically. The connection between geometry and information keeps becoming harder to ignore, and the philosophical consequences are enormous. If space and time are emergent rather than fundamental, then human perception may be filtering reality through a simplified interface shaped by evolution. The world feels spatial and continuous because that representation helps organisms survive, not necessarily because space-time is the deepest layer of existence. Reality underneath could operate according to principles almost impossible for human intuition to visualize directly. This would explain why quantum mechanics feels so unnatural. Human brains evolved to navigate medium-sized objects inside stable classical space-time, not to perceive the deeper informational structure generating it. Even time itself becomes uncertain under these ideas. At fundamental levels, some quantum gravity models do not contain ordinary flowing time at all. Time may emerge only when systems become sufficiently large and thermodynamically complex. In certain equations describing the universe, the deepest level appears strangely timeless. That possibility feels psychologically disturbing because human identity depends heavily on the experience of moving through time continuously. Quantum computers are not proving these theories correct. Most remain highly speculative and incomplete, but they are helping physicists explore regimes where ordinary classical assumptions about space, time, and separateness stop working cleanly. And that may be the most unsettling realization modern physics keeps uncovering. The reality humans experience directly might not be the true structure of existence. It may only be the large-scale surface generated by something far stranger underneath. One of the strangest facts about quantum mechanics is that physicists still do not agree on what the theory actually says about reality. Not because the math fails. The equations work incredibly well. Quantum mechanics predicts experiments with astonishing accuracy. The problem is interpretation. Scientists can calculate outcomes perfectly while disagreeing completely about what is physically happening underneath. And at the center of that disagreement sits the observer problem. The issue begins with measurement. Quantum systems evolve smoothly as probability waves according to the Schrödinger equation. Multiple possible outcomes coexist mathematically in superposition. But when measurements occur, observers see definite results. Somehow, probability turns into reality. But how? No consensus answer exists. The Copenhagen interpretation, historically the most famous view, says quantum systems do not possess definite properties before measurement. The wave function represents possible outcomes, and measurement collapses those possibilities into one observed result. This interpretation works operationally, but many physicists dislike its vagueness. What exactly counts as a measurement? Why should observation trigger collapse? Does a detector qualify? Does the environment? Does consciousness matter? The theory does not clearly say. Many worlds avoids collapse entirely. The wave function never reduces to one outcome. Instead, every possibility continues existing in separate branches of reality. Observers become entangled with outcomes and experience only one branch internally. This removes the mysterious collapse process but introduces an enormous number of parallel realities. Then there is pilot wave theory, also called Bohmian mechanics. In this interpretation, particles always possess definite positions. Hidden quantum waves guide their motion non-locally. Reality remains deterministic underneath, but the theory requires strange, faster-than-light quantum connections built into the underlying structure. Einstein might have preferred parts of this approach because it restores objective properties, though it sacrifices locality. Relational quantum mechanics takes another path entirely. It argues physical properties only exist relative to interactions between systems. There may be no universal observer-independent state of reality at all. Facts become relational rather than absolute. And those are only a few examples. What makes this situation extraordinary is that all these interpretations reproduce the same experimental predictions. That means current experiments cannot cleanly distinguish between them. Imagine multiple people solving a math problem correctly using entirely different stories about how the world works underneath. That is essentially the situation in quantum foundations right now. Quantum computing intensifies this confusion because it forces scientists to engineer systems living directly inside these interpretational tensions. Qubits evolve through superpositions. Entangled systems share non-classical correlations. Measurements collapse computations into definite outputs. The machines work regardless of interpretation, yet every successful operation keeps reviving the deeper philosophical questions. What is a quantum state physically? When does a possibility become an actual event? Does reality fundamentally branch, collapse, or remain relational? No one knows. And this uncertainty bothers people more than many scientific mysteries because it attacks the idea of objective reality itself. Humans instinctively assume the universe exists in a fully defined state, independent of observation. Quantum mechanics keeps resisting that picture. Even worse, different interpretations imply radically different universes while remaining experimentally indistinguishable so far. In one interpretation, reality branches endlessly. In another, particles follow hidden trajectories. In another, properties emerge only through relationships. In another, collapse happens fundamentally but unpredictably. All produce the same measurable results. That creates an uncomfortable possibility. Human intuition may simply be too limited to visualize what quantum reality actually is. The observer problem might feel paradoxical because our brains evolved inside a decohered classical environment where outcomes appear definite automatically. Evolution optimized humans for survival, not for understanding microscopic ontology. Quantum computers are exposing this mismatch more directly than ever before. These machines operate successfully using principles that humans still cannot fully explain conceptually after nearly a century of debate, and that may be the strangest part of all. Modern civilization is beginning to build technology on top of physical laws whose deeper meaning remains unresolved. Once people hear that observation affects quantum systems, the conversation almost always drifts toward consciousness. Does the human mind collapse reality? Could awareness itself shape the physical universe? These ideas became popular partly because quantum mechanics already sounds mysterious and partly because some early physicists spoke cautiously about observers and measurement. Over time, those discussions evolved into books, documentaries, internet theories, and endless claims linking quantum physics to spirituality, manifestation, or cosmic consciousness. But mainstream physics is far more careful. Most physicists do not believe human consciousness is required for quantum mechanics to work. A detector can measure a particle without a conscious observer watching it. Environmental interactions cause decoherence continuously throughout nature. Stars fused elements long before life existed. Quantum processes occurred for billions of years before brains evolved on Earth. So in ordinary scientific terms, consciousness does not appear necessary to create reality. That said, the topic refuses to disappear, completely because the observer problem still lacks a universally accepted solution. And consciousness itself remains poorly understood scientifically. Nobody currently has a complete theory explaining subjective awareness. Neuroscience can map brain activity and identify correlations with conscious experience, but the deeper question of why physical processes produce inner subjective experience at all remains unresolved. This leaves room for speculation at the edges. Some interpretations of quantum mechanics historically flirted with consciousness-related ideas. Physicist Eugene Wigner once considered whether conscious observation might play a role in collapse, though he later moved away from that position. Mathematician John von Neumann also explored frameworks where consciousness entered the measurement chain. But modern physics generally avoids these explanations because they create more problems than they solve. If consciousness causes collapse, what counts as conscious enough? Humans? Animals? Insects? Artificial intelligence? And how did the universe function before conscious life appeared? The idea quickly becomes difficult to define scientifically. Most researchers instead focus on decoherence and information exchange. Quantum systems lose coherence through ordinary physical interaction, not necessarily through awareness. Measurement becomes a process involving entanglement with larger environments, rather than mystical observation. Still, some scientists continue exploring whether consciousness and quantum mechanics might intersect indirectly. Roger Penrose, for example, has proposed controversial ideas suggesting quantum processes could contribute to consciousness inside the brain. These theories remain highly debated and lack strong experimental confirmation, but they show the topic is not entirely dismissed. The key point is this: quantum mechanics does not currently prove mystical claims about consciousness shaping reality, but it also leaves deep philosophical questions unresolved about observation, information, and subjective experience. That uncertainty attracts enormous public fascination, because consciousness already feels mysterious even without quantum physics involved, and quantum computers amplify the conversation. People naturally wonder whether machines manipulating quantum states are interacting somehow with deeper layers of reality tied to observation itself. In practice, quantum processors operate through physical engineering principles, not awareness. They do not think probabilities into existence. Yet these systems still reveal something profoundly strange. Reality appears sensitive to interaction and information in ways classical physics never expected. That alone is enough to make people uncomfortable. Human beings evolved assuming the world exists as a stable external structure, independent of participation. Quantum mechanics complicates that picture by making interaction central to physical outcomes. Not necessarily consciousness, but interaction itself. And because consciousness is the most intimate form of observation humans know, people instinctively connect the two ideas emotionally. The danger comes when speculation outruns evidence. Quantum mechanics is already strange enough without inventing unsupported mystical conclusions. The real science is fascinating precisely because it forces difficult questions while remaining grounded in experiment and mathematics. The honest answer is that physicists still do not fully understand measurement, reality, or consciousness at the deepest level. Quantum computers are not solving those mysteries, but they are making it harder to pretend the mysteries do not exist. At this point, it becomes important to separate real physics from internet mythology, because quantum mechanics is strange enough on its own without exaggeration. The rise of quantum computing has created a flood of headlines claiming scientists proved reality is fake, consciousness controls the universe, parallel dimensions are confirmed, or humans live inside a simulation. Social media made the problem worse because quantum topics generate enormous attention, especially when mixed with fear or mystery. The issue is that many of these claims distort what physicists are actually saying. Quantum computers are extraordinary machines, but they are not magical reality engines. They do not open portals to alternate dimensions. They do not allow people to jump timelines. They do not prove manifestation theories, and they do not show that thoughts directly rewrite the universe. What quantum computing does show is already strange enough. Microscopic systems follow probabilistic rules that differ radically from classical intuition. That is real science. The confusion often starts because quantum mechanics uses language that sounds familiar but means something highly technical. Words like observation, measurement, uncertainty, and information carry ordinary meanings in daily life, but in physics, they describe mathematical and physical processes precisely. For example, when physicists say observation affects a quantum system, they do not necessarily mean a conscious person looking at it. Interaction with detectors, particles, or the environment counts as observation in quantum theory. But once these ideas spread online, technical nuance disappears. People hear observation changes reality and jump immediately to mystical conclusions. Another source of hype involves the many worlds interpretation. Because branching realities sound dramatic, many videos and articles present them as established fact. In reality, many worlds is one interpretation among several competing frameworks. It is mathematically consistent but not experimentally proven over alternatives. The same problem happens with simulation theory. Some physicists and philosophers discuss whether reality might contain informational structures resembling computation. But that is very different from claiming scientists discovered humanity literally lives inside a programmed simulation run by external beings. Speculation often grows much faster than evidence. Quantum computing companies also contribute unintentionally to hype because the field attracts enormous investment. Terms like quantum supremacy and revolutionary computing create excitement, but public understanding often skips over the limitations. Current quantum computers remain extremely fragile. Most systems suffer from high error rates and decoherence problems. Useful large-scale fault-tolerant quantum computing still requires major breakthroughs in engineering and error correction. Researchers are making impressive progress, but practical universal quantum computing remains difficult. That does not make the technology fake. It simply means reality is more complicated than headlines suggest. And honestly, the real science is already unsettling enough without exaggeration. Bell experiments genuinely challenge classical local realism. The double-slit experiment genuinely reveals non-classical behavior. Entanglement genuinely exists. Quantum probabilities genuinely appear fundamental in nature. Those discoveries alone force humanity to rethink some of its deepest assumptions about reality. There is no need to invent unsupported claims on top of them. In some ways, quantum hype reflects a psychological reaction. Humans want clear stories. Either reality is stable and ordinary, or it is mystical and magical. But modern physics sits in a much stranger middle ground. The universe does not behave according to everyday intuition. At the same time, it still follows precise mathematical rules tested experimentally with extraordinary accuracy. Quantum mechanics is not fantasy. It is a scientific framework describing nature so successfully that modern civilization depends on it constantly, even though humans still struggle to interpret what the equations ultimately mean. Quantum computers sharpen that tension dramatically. They are forcing society to confront the fact that the world underneath ordinary experience may be fundamentally probabilistic, relational, and deeply unintuitive. That conclusion does not require supernatural explanations. It only requires taking the physics seriously. After all the interpretations, speculation, and philosophical debate, it is important to step back and ask a simple question. What has quantum physics actually confirmed experimentally? Because despite the mystery surrounding the subject, there are a few conclusions scientists are extremely confident about. First, the microscopic world does not behave classically. This is not theoretical anymore. The evidence is overwhelming. Electrons, photons, atoms, and other quantum systems consistently display behaviors impossible to explain using ordinary classical physics alone. Particles interfere like waves, superpositions exist, entanglement is real, quantum tunneling happens constantly. These effects are measured directly in laboratories every day, and power technologies already built into modern life. Second, local hidden variable explanations appear deeply incomplete. Bell test experiments repeatedly show correlations that classical local realism cannot explain. Something about the universe violates at least one assumption humans naturally expect. Either physical properties are not fully predetermined before measurement, or distant systems are connected in ways classical physics cannot describe cleanly. That result is one of the most experimentally secure discoveries in modern science. Third, probabilities appear fundamental to quantum mechanics itself. In classical physics, probabilities usually reflect ignorance. If you roll dice, uncertainty exists because you lack complete information about forces and motion. In principle, a perfect classical observer could predict the outcome exactly. Quantum mechanics behaves differently. Even with complete knowledge of the wave function, only probabilities can be predicted for many outcomes. Nature itself appears intrinsically probabilistic at microscopic scales. That does not necessarily mean reality is random in a simplistic sense. Some interpretations preserve hidden deterministic structure underneath, but experimentally, quantum predictions remain probabilistic. And those probabilities are extraordinarily accurate. Fourth, observation and interaction matter physically. Again, this does not mean consciousness magically creates reality. But quantum systems clearly respond to measurement interactions in ways classical systems do not. Obtaining information about a system changes the system itself. The double-slit experiment demonstrates this repeatedly. Quantum computing demonstrates it technologically. Decoherence demonstrates it macroscopically. Fifth, information appears deeply connected to physical reality. Modern quantum information theory, black hole research, and entanglement studies increasingly treat information as a physical quantity, not merely an abstract concept invented by humans. Quantum states encode measurable structures that influence how reality behaves. And finally, perhaps the most important conclusion. Human intuition is not a reliable guide to fundamental physics. This may sound obvious, but it is psychologically difficult to accept. Humans evolved for survival in medium-sized environments on Earth, not for understanding microscopic reality. Classical intuition works beautifully for ordinary life because decoherence hides quantum effects at large scales. But beneath that stable surface, the universe operates according to rules that often feel alien compared to everyday experience. Quantum computers matter because they push these conclusions out of abstract theory and into engineering reality. These machines are not philosophical thought experiments anymore. They are physical systems built around superposition, entanglement, interference, and quantum information processing. Every successful operation reinforces the idea that the strange predictions of quantum mechanics correspond to something physically real about nature. What scientists still debate is interpretation. Does reality branch into many worlds? Do wave functions collapse fundamentally? Are properties relational? Do hidden variables exist non-locally? No consensus exists yet, but the experiments themselves already narrowed the possibilities dramatically. The universe does not seem to behave like a giant deterministic clockwork machine underneath appearances. At deep scales, nature appears probabilistic, interconnected, and resistant to fully observer-independent classical descriptions. That is the part quantum computers are forcing society to confront. Not because the machines invented new physics, but because they are making old physics impossible to ignore anymore. By now, the real picture starts becoming clear. Quantum computers did not suddenly discover that reality is horrifying. Physics has been quietly pointing in that direction for almost a century. What changed is that humanity can no longer keep those ideas trapped inside theoretical debates. Quantum mechanics is no longer just strange mathematics written on university chalkboards. It is becoming technology. Engineers are building machines that function only because the universe behaves in ways human intuition was never designed to understand. And that may be the deepest, unsettling part of all. Humans evolved inside a very narrow slice of reality. Our senses are tuned for survival at human scales. We intuitively understand falling objects, moving animals, solid surfaces, and ordinary cause and effect relationships because those patterns mattered evolutionarily. The brain built a stable, simplified model of the world that helped organisms stay alive long enough to reproduce. Nothing in evolution required humans to perceive fundamental reality accurately, and modern physics increasingly suggests we do not. Quantum mechanics keeps revealing a universe where certainty dissolves into probability, where separateness becomes entanglement, where observation and interaction cannot always be cleanly detached from physical outcomes, and where even space and time may emerge from deeper informational structures underneath. That does not mean reality is magical or supernatural. In fact, the most disturbing part is how mathematically precise it all is. The equations work, again and again. Quantum theory predicts experiments with astonishing accuracy while simultaneously refusing to fit comfortably into ordinary human concepts about what existence should look like. People often react to this in two extreme ways. Some reject the weirdness completely and insist there must be a hidden classical reality underneath waiting to be discovered. Others leap too far in the opposite direction, turning quantum mechanics into mystical fantasy disconnected from science. But the real situation is stranger than either extreme. Physics is not telling humans that reality is imaginary. It is telling us that the universe may not organize itself according to the categories human brains evolved to expect. Classical reality, the stable world of objects, locations, and definite events, appears increasingly like an emergent surface layer created through decoherence, interaction, and scale. Underneath that layer sits a deeper quantum structure where probabilities, information, and entanglement dominate. Quantum computers force society to confront this directly because they exploit those deeper rules operationally. Every successful quantum computation acts like a reminder that the microscopic universe is not behaving classically behind the scenes. The weirdness is not an illusion caused by incomplete measurements anymore. It appears deeply woven into how nature operates. And perhaps the most psychologically difficult realization is this: reality was never obligated to make intuitive sense to human beings. The universe does not care what feels natural. Earth feels motionless even though it spins through space at enormous speed. Time feels universal even though relativity shows it bends with gravity and velocity. Matter feels solid even though atoms are mostly empty space. And reality feels definite even though quantum mechanics suggests uncertainty may be fundamental underneath. Again and again, science keeps revealing the same uncomfortable truth. Human perception is not the final authority on existence. Quantum computing may become one of the greatest technological revolutions in history, but philosophically, it is doing something even more important. It is exposing how limited human intuition really is. The horror is not that reality is broken. The horror is that reality may have always been far stranger than the human mind can naturally comprehend. Watch the next video.